Good afternoon, everybody. My name is ČULIĆ from the University of Split, Croatia, and I would like to present you my paper where I presented my work on investigation of personal thermal comfort, a case study from university building, which I wrote with the assistance of my supervisors, Professor Sandro and the rest of the team from the University of Split, Professor Petar ŠOLIĆ, Professor Toni PERKOVIĆ, and Dr. Jelena ČULIĆ GAMBIROŽA from my university. To bring you this topic a little bit closer, I would like to mention the evolution of the buildings through the time. And all the time innovative technologies are being developed for integration into buildings and into building management systems. And in the recent times, novel technologies are leading to smart building development as a part of smart city concept. And through this concept, the important role of the occupants has been recognized, since the users in the buildings have a very big impact on energy performance in the buildings, which has been also acknowledged through the some studies in the field. And also some user-centric technologies are being developed also in this domain in order to provide energy-efficient indoor environment for the users, while considering the human aspect in the building performance as well. When talking about the heating, cooling, ventilation and air conditioning systems in the buildings, users' thermal comfort has been highlighted as very important aspect to be considered during the operation of these heating, cooling, ventilation and air conditioning systems. So, through the literature so far, different studies have addressed this thermal comfort issue, trying to enable optimal conditions for reaching thermal comfort of the users in the buildings. To be more specific, some studies are creating some personal adjustable environments to the users, which means they are providing some local heating and cooling to the users in some local area around them. Or also some studies are developing a data-driven approach, which relies on the collection of relevant thermal comfort parameters through some sensing devices, and then based on the inputs developing some modeling and operating logic to the heating and cooling system. So for the study which is presented herein within this work, we have relied on this data-driven approach for investigation of thermal comfort conditions of the users. The experimental framework for assessing personal thermal comfort was established in the University of Split, Faculty of Electrical Engineering, Mechanical Engineering and Naval Architecture in Croatia. And the experiment was conducted for the heating period in 2 faculty offices on 6 subjects, 3 female and 3 male subjects. The premise for the conducted experiment setup was data-driven thermal comfort approach with the application of smart technologies. Our approach included measurements of ambient parameters, users' physiological parameters, and the subjective feedback from the users regarding their evaluation of the indoor thermal conditions. Environmental conditions were monitored with indoor ambience monitor sensor, which included different sensors such as air temperature, relative air humidity, carbon dioxide level, volatile organic compound, barometric pressure, light intensity, motion sensor, and also we have included particulate matter sensor, while on the other hand, users' physiological parameters, more particularly heart rate and wrist skin temperature, were monitored at the same time with the Global Sat LoRa 1 smart watches, which were placed on the user's wrist during the working day. In order to collect complete information about thermal comfort, users' feedback was also considered. Subjective evaluations were gathered through the online survey that utilized a 7-point thermal sensation scale every hour during the working day, and users were included in the experiment within their own work schedule to avoid any additional external psychological pressure to the subjects and to enable them uninterrupted work. Users during their time at the work, they were instructed to assess their thermal sensation questionnaire on a scale from -3, which represents feeling cold, to +3, which represents that they are feeling hot in the given environment, with neutral sensation signifying a number 0 in data processing. The main goal of the herein presented experiment was to set up a network of sensors for continuous monitoring of ambient and user-related parameters, such as heart rate and wrist skin temperature during a working time in office, and collecting users' subjective evaluation of the thermal environment. Further on, collected data can be used to create some important basis for further investigation of the interrelations among collected subjective users' evaluations and the measured parameters from sensors. Therefore, the objective of the herein presented research is to explore whether the application of smart devices can significantly contribute to thermal comfort modeling, and also could it provide some assistance in the development of intelligent heating and cooling system and management models for the heating and cooling systems in the buildings. For adequate data processing, a data set should have been extracted from all the gathered information during the experiment period. A Python programming language was used for the purpose of data processing, and the analysis was performed in the Jupyter notebook. Within herein presented research work, 9,912 rows of data for all 6 users were collected during the experiment, and the distribution of data by user is presented in the table 1, where it is obvious that the amount of data for each user during the experiment was between 1,500 and 1,800 rows of data after we done all of the cleaning of the redundant and unuseful data. To provide meaningful results, we have divided this section into 2 parts. As a first part, we provided data analysis and visualization, while as a second part, we have provided our approach in predictive modeling. Data visualization was carried out for each office and with respect to every user separately, considering main indoor ambient variables, more specifically air temperature, air humidity, and carbon dioxide level, and also we have included user physiological parameters, more specifically heart rate and wrist skin temperature, which were extracted and visualized per user in each office with respect to the thermal comfort responses of the users. On the charts presented on this slide, air temperature relations are presented with respect to the users' answers about their thermal comfort evaluation, which are presented with these colorful circles. And also on charts we have shown what are minimal, maximum values, and also mean and median for air temperature. And in the all following charts, the same logic is also applied. From the charts about air temperature on this slide, it can be concluded that for the same temperature, for the same air temperature, each user can give a different subjective evaluation, and also one person has evaluated the same temperature differently in multiple occasions. Although each user has its own subjective evaluation of the indoor air temperature in the office, for the higher air temperatures, warmer thermal sensations have been recorded by the users. So these charts can give us information that some more additional information would be valuable to find some more in-depth correlations between users' answers and their thermal comfort and some measured parameters from the sensors. These charts are representing the relation between air humidity and relative air humidity in the office and users' thermal comfort responses, and no visual nor numerical correlations were found with the relative air humidity and general thermal comfort responses from herein presented data set. Further on, the charts on this slide are presenting the relations between carbon dioxide level and the user's thermal comfort responses, and also it is different among each user and among the offices. However, some slightly sensitivity of carbon dioxide level and users' thermal comfort responses are visible, especially on the charts for Office 2 and on the chart for Office 1. And also it is worth noticing that user 4260 seems to be some kind of statistical error, since he has mostly red answers for each chart presented so far. Further on, we have also included and visualized wrist skin temperature values with respect on thermal comfort responses from the users, and it can be visible from the charts here presented that user 4260 has reported most of the values in the warm spectrum. Further on, users 4261 and 4272 did not have many warm sensations, while user 4272 had most of responses being 0, which represents neutral subjective sensation. Other users have reported diverse distribution of their thermal sensation answers without visible dependency on the wrist skin temperature, as presented on the charts here for the both offices, Office 1 and Office 2. Heart rate values are user-specific and differ for each user. However, tendency for warm thermal comfort responses increases with the increase in the heart rate value. The charts of thermal comfort responses with respect to measured heart rates of the users are presented on the figures on this slide, which show the interrelations between these two values. Our data set contained 17 features for 6 users in 2 offices during winter, which means heating period. And as visible from the figure on this slide, our data set was not well balanced because users most commonly reported neutral thermal sensation, followed by value number 2, which represented warm thermal sensation. So in order to provide balanced data set for further data processing, we used undersampling method, which means removing some data from majority of classes, and also to provide better data ratio, we have divided the answers in only 3 classes instead of 7 classes as it was provided by the thermal sensation questionnaire. And also data was split in train and test set chronologically, which means that first 80% of inputs are used as train set, while the last 20% chronological inputs are used as test set in our data. In order to build predictive machine learning model, in this study we have applied random forest classifier. Finding optimal hyperparameters was done by performing a grid search, and the best accuracy of 60% is achieved with hyperparameters in the given table on this slide. The optimal hyperparameters are presented in red color on the table 2. Results are presented in the confusion matrix on this slide. As it is visible from the confusion matrix, hot and cold classes are fairly recognized in 67.5% cases, but class 0, however, has accuracy of 49%. Therefore, for 120 inputs, herein presented a random forest algorithm correctly predicts a user's thermal comfort 72 times in 60% cases. The low accuracy of comfortable class may be due to different thermal comfort for different users and even different thermal comfort for the same user given same parameters. So, to sum up, in the herein presented work, we have provided the description of experimental framework for evaluating individual thermal comfort, which was conducted in the university building in Croatia, based on data-driven thermal comfort paradigm, incorporating smart technologies. Our data set collected through the experiment was not well balanced because users most commonly reported optimal thermal comfort response, and we needed to provide better balanced data set. In this study, we applied undersampling method, which means removing some extra data from classes that had too much data in comparison to the other ones. Also, to provide better balanced data set, we merged the potential classes into 3 categories based on the thermal preference responses provided by the users. And also, we had divided our data set chronologically, which means that first 80% of inputs were forming the training set, and the last 20% of the data chronologically formed the test set. For the model prediction, we applied random forest algorithm, and with the best hyperparameters, random forest algorithm recognizes hot and cold classes in 67.5% of cases, while still it has a challenge with class 0, which represents comfortable thermal sensation, which had an accuracy of 49%. So, for some future work, we are focused towards gathering more data during the summer period for cooling data, and also more data on more users. Further on, we need to explore some alternative balancing techniques or evaluation metrics to provide a better balanced data set on more data for constructing individual machine learning models for each users based on their unique comfort preferences. Also, in this herein presented work, we didn't use closing level data, so for some future work we should incorporate closing level data also into the model, and further on different machine learning algorithms other than only random forest should be considered as well. So that's all from me for now. If you have any questions or suggestions regarding my topic, I would be glad to answer you and to hear your thoughts on my work. Thank you one more time for your attention.